This brief lecture provides a gentle introduction to structural Verilog, which is used to describe digital hardware. Verilog has been around for several decades, and like most computer languages, it has evolved over time into a very powerful and useful yet dangerous beast. Since this is your first exposure to the language, we will introduce just a small subset of it to keep things manageable. Specifically, we will cover only a subset of what is known as structural Verilog. It is called structural because it is very close to the structure of the hardware that it describes. Verilog also has behavioral features, which are included to enable describing the behavior of the hardware rather than its structure. This lifts the level of abstraction of the language, making it more flexible, powerful, and concise, but also more complex and messy. Hence, it is too much for this introduction, so we will leave it for later. Verilog as a language has two main purposes. First, to enable designers to describe the hardware they want to build. This is why it is known as a hardware description language, or HDL. The other HDL in common use is called VHDL, which is in many ways similar to Verilog but differs in most of the syntactic details. Verilog is also used to write software that tests the hardware being designed, using something called test benches that run in simulation. These two purposes are very different, but confusingly, Verilog provides overlapping syntax for them. This leads many students of Verilog astray, leading them to confuse the describing of hardware, the first use, with the writing of computer programs, the second use. This is an understandable confusion due to the similarities in syntax between these two uses. However, it is best to keep this distinction in mind and remember that unless you are writing test benches, which you will do later but not in this introduction, you should stick to elements of Verilog that describe hardware. Sometimes this distinction is described as synthesizable Verilog versus non-synthesizable Verilog, which in itself is confusing, but is intended to convey the idea that some Verilog features cannot be practically converted or synthesized into digital hardware and can really only be used during simulation. This is true, but in my view, it is more helpful to break things between hardware and software, and to then remember that the non-synthesizable features of Verilog should only be used in test benches, which are software, and not in the hardware descriptions themselves. In this lecture, we will focus strictly on Purpose 1, which is describing hardware, and will not introduce or explain any Verilog features that are used solely for Purpose 2, software that tests hardware in simulation. So what is structural Verilog? As mentioned already, it is a simple subset of Verilog that closely matches the structure of the hardware that it describes. You can think of structural Verilog as a text-based version of logic schematics. This is sometimes also called a netlist because it lists all of the nets or signals, all the gates, and all the modules in a design and captures how they are wired together. Designs in structural Verilog are hierarchical in nature, meaning they have modules of modules, which are also made up of modules, and so on. You get the idea. The main advantages of Verilog over schematics are obvious. Since the Verilog is stored in a text file, you can use your favorite text editor to edit it. You don't need a graphical user interface. You can easily search, find and replace, and copy and paste Verilog code. Also, as we'll see in some examples, you can insert comments and use meaningful names for signals and modules. Finally, Verilog is widely used in industry, so learning at least some Verilog will give you a leg up over other candidates searching for jobs or internships. We will introduce structural Verilog via examples that highlight key concepts in the language. The first key concept is nets or signals. In System Verilog, the latest and recommended standard version of Verilog, nets are declared with the keyword logic. Earlier versions used wire or reg. Do not use these as they are a bit confusing and poorly conceived. Logic nets can be named just like variables in high-level programming languages, but they do not behave like variables since they only live in the moment. Remember that hardware continuously evaluates, so a logic net takes on whatever value your circuit assigns to it. The second key concept is built-ins, which include familiar gates like AND, OR, XOR, and NOT. There are many other built-ins, but for now we will stick to the subset shown here. A gate can be instantiated as shown above by declaring the gate type, giving it a name, and then identifying the nets that are used as output, the first one listed, and one or more inputs. In Verilog, we call these arguments ports. They look like parameters in a high-level language function call, but they are not that at all. In a program, a function is called at some point in time as the program executes. In structural Verilog, an instantiated gate is always present and constantly for all time evaluates its inputs to generate its output. The next key concept is a module. A module declaration gives a name to a new type of module and lists the ports that it uses to communicate with the rest of your design. Ports are either inputs or outputs. There is also a third port type, which is bidirectional, but we will learn about that later. A module also contains its implementation, which consists of nets, declared as logic, and gates. For simple gates, the ports are connected based on their position. The first port is the output, and all subsequent ports are inputs. This is allowed for more complex modules as well, but it is heavily discouraged, as it is very error-prone. In a moment, we will see a better example that connects ports by name. The example shown here is a full adder, which requires a 3-input XOR gate, 3 2-input AND gates, and a 3-input OR gate to generate the sum and carry outputs. As you can see, a structural module implementation is pretty much just a list of gates and nets, hence we can think of it as a netlist. Note also that we can insert single-line comments into Verilog. Anything following a double slash is ignored when the HDL is simulated or synthesized into hardware. Connecting primitive built-in gates to implement combinational logic is quite painful. There is a much better way to do this, which is the assign statement. An assign statement has a left-hand side, which is the output of the combinational logic that it describes, and a right-hand side, which provides an expression that describes the combinational function implemented by the assign statement. The right-hand side looks a bit like Boolean algebra, but the operators are all different. Unfortunately, Verilog supports arithmetic operations as well as Boolean operations and reserves operators like plus and star for addition and multiplication. So Boolean operators use what is shown here: an ampersand for AND, a vertical line for OR, and a caret for XOR, and a tilde for NOT. The expression can also contain parentheses to properly group and prioritize operations. There are also many other operators supported, most of which we will not cover here. This example of a full adder illustrates how much more concise and readable assign statements are when compared to the gate-level structures shown on the previous slide. As a final note, keep in mind that even though assign expressions look a lot like assignments in common high-level programming languages, they are not the same thing. They are converted into gates and nets and evaluate constantly, unlike assignments in programs, which evaluate only when the program executes them. Hardware descriptions, even though they look similar to high-level language programs, are not software. Conditional expressions are a powerful mechanism for implementing conditional operations in Verilog. They are implemented with a ternary operator. Ternary means that it takes 3 arguments, which has a first argument that specifies a Boolean condition, followed by a question mark, followed by a left and right value separated by a colon. The conditional expression will assign either the left or the right value to the left-hand side, depending on the value of the condition. This example implements a 2-to-1 multiplexer, where the SEL input determines which of the 2 MUX inputs, MUX 0 or MUX 1, is routed to the MUX output. We'll see a more complex example of a conditional expression in just a bit, which will demonstrate that the left and right values can also be expressions, even conditional expressions. Note also that we can add multi-line comments in Verilog using the /* to open a comment and the */ to close a comment. Often in hardware designs, we need to group multiple signal bits into a single bus or vector. Verilog supports this using the square bracket notation shown in the example. The first and last number inside the square brackets specifies the index of the leftmost or most significant bit and the rightmost or the least significant bit in the vector. And the size of the vector is the inclusive distance between these numbers, i.e. subtract the 2 numbers and add 1. Individual elements of a vector are accessed with a subscript, and we can even specify subsets of the vector, as shown on the slide. Vectors are a very powerful and useful syntactic feature that can be applied to inputs, outputs, logic nets, as well as modules. We will see more detailed examples of these capabilities in a few minutes. In assign statements, vector arguments to operators like AND, OR, and NOT will be processed 1 bit at a time, so that the most significant bit of the left-hand side is set to the most significant bit of each argument applied to the Boolean operator. These are known as bitwise operators. Verilog also supports a unary form, for AND, OR, and XOR. Unary means the operator only has a single argument instead of two. In unary form, all the bits in the vector are treated as arguments to a single gate of the type specified. This lets us concisely do things like check to see if all the bits in a vector are 0 by performing a unary OR of the vector and complementing the result. Another key concept in Verilog is how we specify literal values. Verilog is very picky about the width of signal nets and requires literals to also specify their width explicitly. This is done using the notation shown in the example, where a 2-bit literal is prepended with a 2 followed by an apostrophe, and a 4-bit literal is prepended with a 4 followed by an apostrophe, and so on. The simulation and synthesis tools will typically detect mismatched widths in your assignment statements and generate warning messages. Do not ignore these warnings. Instead, fix the mismatches right away. Literals can be written in binary, hexadecimal, or decimal by specifying the B, H, or D prefix before the literal value. The example here implements a 2 to 4 decoder and highlights the equality operator, double equals sign, which can be used to determine the outcome of a conditional expression. We can also see here how conditional expressions can be nested within each other to implement multiple condition checks in a single assignment statement. Pay attention to how the parentheses are used here to group the conditional expressions correctly. A key feature of Verilog is its support for modular design. We can construct modules out of other modules, which can further be constructed out of other modules, and so on. Here we're looking at an example that builds a 4-bit carry propagate adder from 4 full adders by connecting the carry out from each full adder to the carry in of the next bit position. Note that we declare a carry vector of size 3 for these carry signals and then connect elements of that vector to the appropriate ports in each full adder module. Here we are also connecting ports by name using the syntax shown. As you can see, this is much more readable than the positional approach and also much less likely to introduce errors, so you should use this port connection method at all times. This example also highlights that all module instances must be given unique names. Verilog also supports a powerful concept called concatenation, which allows us to construct vectors of bits out of some combination of subvectors, individual nets, and literals. The first example shows how to use concatenation to implement a left shift by 1. The leftmost bit is dropped since only bits 2 to 0 of A are used in the concatenation, while a literal 0 is appended to replace the least significant bit. The second example shows a right shift operation, which is very similar to left shift, except the least significant bit is dropped, and a 0 is inserted into the most significant bit. The third example shows an arithmetic right shift, where we perform sign extension to make sure that right-shifted negative numbers stay negative after the shift operation. This is accomplished by repeating the sign bit twice as the first component of the concatenation operation. This example introduces the repeat operator, which gives us a convenient way to replicate individual bits or vectors of bits as part of a concatenation operation. Concatenation is frequently used in scenarios where vectors of modules are being instantiated. Verilog supports automatic wiring of vector entries to ports of the module that is being instantiated as a vector. In this example, which is similar to the earlier 4-bit adder, we instantiate a vector of full adders instead of 4 separate adders. The A, B, carry in sum, and carry out ports are automatically connected to the corresponding elements of the vectors named in the instantiation. However, in this case, we need the carry-in vector to include the externally supplied carry-in provided by the cin input to the adder 4-bit module. We accomplish this by concatenating it with the carry-out signals generated by the 3 least significant full adder modules. In this way, each vector full adder module gets the correct connection for its carry-in values. As you can see, this notation enables very concise and readable instances of multi-bit data paths. The final concept we introduce here is a D flip-flop, which is used as the sequential storage element in structural Verilog designs. Unfortunately, Verilog does not include this as a standard built-in element, but we will provide a module implementation for you to use in your designs. We show only the module interface here, as the implementation portion requires behavioral Verilog, which is beyond the scope of this lecture. Due to Verilog's modularity, you don't need to see or even understand the implementation. You can just instantiate DFFs whenever your design needs them. As you can see, The interface matches a standard DFF with a D input, a Q output, and clock, reset, and enable control pins. Once again, you can use vector notation to create a one-dimensional register from this simple building block. Here, the Verilog compiler is smart enough to know which ports remain scalar, the clock, the reset, and the enable signals, and which ones are vectors, D and Q, by considering how they are declared in the enclosing register 16B module. This concludes our brief introduction to structural Verilog. Please make sure you review the key concepts that are listed on this page and go back and revisit the examples shown to make sure you understand how each of these is used.